Alrighty. So I was hoping to have the next project ready. It's not ready, so that's okay. Hopefully it'll be ready tomorrow. I can talk about what we're going to be doing for the last project. And so anyway, we're going to do part 2 of memory management in C++. So last time we went through constructors, destructors, copy constructors. Look, all my pretty red lines. You know, my wife gets mad at me when I make these slides. She's like, put some color in there. Even just make it. It's like, there is color. You see the color? It's all red. I know, these are really boring slides, and I'm sorry, but it's really the only way I can do this. Talked about move constructors and the rules of 0, 3, and 5. All right, so to continue this, I want to talk about the relationship between copy constructors and move constructors. And the important thing here is that implicit move constructors, or the ones that are made by the compiler, are only generated if all of these conditions are met. There are no user declared. So basically there's no copy constructors that you have declared. There's no move constructors that you've declared. There is no destructor that you've declared. And the move constructor has not already been implicitly deleted. So if your class contains something that has a deleted move constructor, you can't move it because it has something in it that can't be moved. So the important thing here is that if you were to write just a copy constructor and a copy assignment, your class will work just fine. All right? Because up until 2011, that's all they had. They didn't have anything else. It will not, however, be able to use move operations because you've omitted them, okay? And it's actually really hard to find these rules. It took me a while. Implicit copy constructors are not generated if you have move constructors or if you have an object where the copy constructor has been deleted. So you can have one or the other or both. Okay. Anyway, the interesting thing about this is that you can create classes which can be moved but not copied. And so that's how you can prevent expensive copies. So, for instance, this right here, that is a copy. Okay, we're saying A is equal to B, and we want to copy B into A. However, that's not possible if we have a movable but not copyable class. Okay, but we can move it. Okay, and the standard library has this handy dandy little function here called standard move. And what this does, literally, quite literally, is this. Does static cast, and I drew an ampersand yesterday. That's really all it does. So it basically takes this L value here and casts it to an R value, at which point the compiler recognizes, oh, this is an R value, so I should use the move constructor instead of the copy constructor. Okay? So what this does is it takes the object stored in B, moves it to A, and then sets B to some default state. Okay? And the question is why would we want to do this? Oh, Well, the answer to that is on the second slide. But first we need to go through this. Something known as copy elision or elision. I don't actually know how to pronounce it. It's also known by the return value optimization. And this is a cheater move by the compiler. They skip the copy/move altogether. And this is allowed as long as the compiler can ensure the result will be the same. So if you remember, I drew my function here. It's used mostly in return values. If we're returning some object A, okay, so we have our return and it's going to get copied across or moved, depending on the situation. It gets copied across the function boundary. But copy elision, or whatever it is, the return value optimization, what it does is, instead of creating A in this space here, it actually just creates A in this space here. So it doesn't have to do any copies at all. However, this is a compiler optimization. It's not reliable. It is done most of the time now with modern compilers. And there are flags. You can turn it on, turn it off if you think it's causing problems. So anyway, the answer to my question here, why do we want a movable but not copyable class? The answer is here. Move constructors were invented for one purpose, I'm pretty sure. And that is, they wanted something called a unique pointer. The C++ people. A unique pointer, in all respects, acts like a normal pointer. You can dereference it. You can use the little arrow thingy. You can. I don't know. I don't think you can do pluses on it. That doesn't make sense. But it works like a normal pointer. But what it does, it's called a smart pointer. What it does is it encapsulates, enforces the idea of ownership while providing automatic cleanup of the resource being the thing that it's pointing to. Okay, so we have our unique pointer here, and it points to a particular resource. Now, it's called a unique pointer because the way the rules of the ownership work is that can be the only pointer pointing to it. And it owns it, and it's in charge of it. And when it's time for it to go, it will delete it for you. So you don't actually have to call delete at any point, because the destructor of the unique pointer will do that. An unique pointer is movable, but it is not copyable. Therefore, the object it points to also cannot be copied. All we can do is change the ownership of that object. So I have some example code here. So here we have a unique pointer. I'm going to call it A, and we're going to make it point to a new double. Okay? And here we can dereference A and set that value equal to 2. All right? So here we now have a new unique pointer. It's currently not pointing to anything. However, this line here, this would invoke a copy, and this is illegal. Cannot be done. But we can move it by using this syntax here. What this does is B now points to the resource. So let me draw my boxes. I love boxes, don't you? Okay, so A is pointing to 2. Okay. At this point here, when we invoke this move, A no longer points to the 2. Instead, B points to it. So B points to the 2. A has been reset to a null pointer. Now, I actually typed this up wrong. There's supposed to be an ampersand here. Okay, that's better. So we can pass B by reference there, which is fine. This just grants temporary access, just like any other reference. However, if we wanted to pass by value, we can't do that, because that invokes the copy constructor. We would have to copy the unique pointer into the function. However, we can move it, and so we specify that we want to move it into the function, which is defined up here. This is legal. However, now the function C here, when we do this, B no longer points to the 2. We've changed ownership. Now C is pointing to the 2. And then when C goes out of scope, when the function exits, it says, oh, we must be done with it, and it deletes the whole thing. Okay, so that's how the ownership, only one unique pointer can point to it at a time. That's the concept of the unique pointer. And the reason it's important is it manages the memory for us. Its job is to say, I own this resource, and when I am dead, then I will delete that resource. Now there are other types of ownership. And so the other important type is the shared pointer. And the shared pointer is used when ownership should be mutual between different parts of the code. When one part could be deleting things or getting rid of things, but we don't want to copy this resource here. So if this is our resource and we have shared pointers, we can have a bunch of shared pointers all pointing to it. And let's say, for whatever reason, C gets deleted. Okay? It goes out of scope or whatever. We don't want the resource to be deleted because we still have A, B, and D pointing to it. And so it doesn't. The way it actually implements this is it actually has a little counter here. And it keeps track of how many pointers are pointing to it. And so when C goes out of scope, we're down to 3. If D goes out of scope, we're down to 2. And B goes out of scope, we're down to 1. Now when A gets deleted, it drops to 0. At which point A says, okay, well, I'm dying, and there's nothing else pointing to this, so now we're going to delete the resource. Okay. And this is what's known as reference counting. And so the 2 is never copied. When you copy a shared pointer, all you're doing is making a new pointer pointing to the same thing. And that's how you keep from making big, expensive copies of really big classes. So when all of the shared pointers die, then and only then is our resource or object deleted. And here's an example, some example code. Very similar to the other one. We have a shared pointer, points to a new double. Again, it acts just like a normal pointer. We can dereference it. And then we make a new shared pointer. And this, remember, in the case of the unique pointer, this was illegal. But now it is, because we can copy a shared pointer. By reference, and again I have the same typo up here. supposed to be a reference in there. And that's fine. Doesn't change anything. But if we pass b by value, that makes a copy. And so now we have c over here also pointing to the same thing. So once this function exits, c gets deleted. It no longer exists. But we still have a and b pointing to 2. And so the 2 does not get deleted. And then we can manually erase the shared pointers, and at which point then the 2 gets taken with the very last one. There is also a weak pointer. So if we have our shared pointers here, a and b, we can have also a weak pointer. And so we'll just draw this weak pointer here. The weak pointer does not increase the reference count. So this still says there's only 2 pointers pointing to this resource, when technically there's 3. But before we can use the weak pointer, we actually can't. You can't dereference a weak pointer. In order to actually use it, you have to convert it into a shared pointer. And so we convert this into a shared pointer, at which point we now have 3 shared pointers, like so. There are good reasons for doing this. It's used to grant temporary access to a shared pointer resource. So if I have a piece of my code and I'm working with a library, which I actually am for my dissertation. So I have a CFD library which returns a shared pointer to pieces of a CFD mesh. Okay. If I kept a shared pointer, first off, I would prevent the library from deleting that piece of the mesh. And secondly, I wouldn't know that that piece of the mesh had been deleted by the library. So by using a weak pointer, I can test. I can say, does this resource still exist? Does this piece of the mesh still exist? Because the conversion to the shared pointer will fail. It'll either throw an exception or give me a null pointer. There's 2 ways to do it. So then I can say, oh, this piece of the mesh is gone, so now I need to do X, Y, and Z. And again, so here's some examples. We have our shared pointer. We create a weak pointer based on that shared pointer. And then if we needed to actually use it, we could do the lock, use the lock function, which returns a shared pointer. And then we reset C, we reset A, at which point now there's no more shared pointers, the resource is gone. And so then if we tried to make our shared pointer from our weak pointer again, this actually would throw an exception because the resource is gone. So those are the 3 major smart pointers. But what about a normal pointer, or as otherwise known, a raw pointer? Raw pointers are actually still useful. And if we consider them from the perspective of ownership, a raw pointer can be used if a particular class does not own the resource. It's not in charge of it. And it is known that the resource will always be available. It's not going to get deleted under our nose. So they are still useful. I use them. And yeah. However, if it's possible that the resource could get deleted and you wouldn't know about it, then you should be using a shared pointer or a weak pointer instead. And then for most cases, what you're going to want to use is a unique pointer. If you need to access the raw internal pointer, you can get it out of there using the get function, and then pass that around to different parts of the program. Say, here, you can take a look at it. You're not in charge of managing it, so that's fine too. So, the big thing that the C++ people want to do with all of this is that with the smart pointers and these standard library containers, your vectors, your lists, etc., you can write classes that manage resources, and you never have to write a constructor or a copy constructor or a move constructor at all. You don't have to worry about it because the resource management, the memory management, is being handled by the smart pointers and by the containers. If you have a unique pointer in your class itself, you can auto-magically have a movable but not copyable class. By putting that in your class, it automatically cannot be copied because the unique pointer cannot be copied. And then the general rule of thumb, what the C++ gurus love to talk about, is that you should never, ever, 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 ever allocate any memory using new or deallocate it with delete. Okay, you should let the memory management tasks be handled by the smart pointers and the containers. So in C++ 11, they have this function here, make shared. Okay, what this does is it makes a shared pointer. In this case, a double, and it initializes it to 2. There is no make unique in C++ 11, and I looked up why, and the answer is they just plain forgot about it, which kind of seems like quite the oversight, but there it is. So they put it in the 2017 standard, and so if you can't use the 2017 standard, you're going to do this instead. You say auto p equals unique pointer double, and then you say new double, and we want to initialize it to 2. Okay, and you can throw whatever constructors you want in there, and it'll work just fine. So anyway, that basically, I mean, I'm not an expert, but I think that sums up how you correctly handle memory management in C++. It's complicated, I know, but the answer is use the smart pointers, use the built-in containers with the standard library, and you should be pretty much good to go. You shouldn't have too many issues. This will eliminate many of your memory leak issues. This will eliminate many of your seg faults. Of course, you could still overstep things, but that's why we use iterators. Iterators prevent us from overstepping our bounds. And in the end, everything gets cleaned up nicely, and you don't have to worry about it. So anyway, that's my lesson for today. And yeah, I haven't heard much. I've had one project get turned in, but I haven't really heard much from anybody on the project, so I'm going to assume it's all going well. Anyway, it was the 4th of July weekend, yes, so that could be screwing people up. Yeah, hopefully I'll have the project ready for tomorrow, and we can talk about that. Anyway, we'll talk to you guys later.